Hello everyone and welcome to Past Chem class. Today we are going to be learning the fundamentals of reading and writing organic chemistry. First, we will talk about the main elements that you will see in OChem. Next, we will revisit the octet rule from general chemistry and talk about how that applies to bonding, referencing the periodic table for valence electrons. After, we draw the structural formula for the molecular formula C3H8. Next, we will discuss the differences and similarities, pros and cons of structural formula, bond line structure, and condensed formula. Then, we will go back and relate the octet rule discussed to single, double, and triple bonds. And lastly, we will practice drawing like an organic chemist. So make sure you have a pencil and paper because you're going to do this right alongside me. Let's get started. Please hit like so I know it's popular, and subscribe so I can keep bringing you OChem videos. Some of the main elements we will be working with in OChem are these. We're going to focus on carbon, hydrogen, oxygen, nitrogen. Carbon itself is so important and prevalent that we draw it as a line to make our lives easier. Hydrogen is also very prevalent, but is a little bit more like a penny. It's so common and less important that most of the time we don't draw it at all. So moving on to C3H8. What does that mean? The subscript 3 means that there are 3 carbons. And most of the time, carbons are attached to each other. That's what those lines mean. That is called a single bond, but we'll get to that later in this video. If you remember from Gen Chem, carbon and all elements in general like to have 8 valence electrons. It's called an octet. If we reference a periodic table, we will see how many valence electrons they come with. These red numbers that you see appearing over the top are called group numbers. They are the same number that correspond with the number of valence electrons these atoms have. So if we find carbon, there it is, the group number is 4. That means it has 4 valence electrons, which means it's missing 4 valence electrons. So if we look at carbon in this way, we see that it has 4 and it's missing 4, which means it's going to want to make some bonds to fill in those holes that it has. If it makes 4 bonds, it will have a total of 8 electrons. Let's look at a few more elements to see what I'm talking about here. The next one we're going to talk about is nitrogen. If we look for nitrogen on the periodic table, it has a group number of 5. That means it has 5 valence electrons. Therefore, it is missing 3 valence electrons. You can see here on the left that it has 2 electrons that are its to keep. It's a nice pair. The next 3 are wanting to bond. So these 3 electrons, if it gives it to a bond, then it will gain another electron in a bond, shown by this empty dot. It's waiting to be filled by another atom's electrons. So nitrogen is going to want to make 3 bonds. I'm going to have a quick note here. It can make 4, but we're going to talk about that another time when we discuss formal charge. Let's talk about oxygen. If we find it on the periodic table, it has a group number of 6, which means it has 6 valence electrons, meaning it's missing 2. If we rearrange these here, we see that it has 2 pairs of electrons that it gets to keep, and it has 2 electrons that it wants to share to a bond to get 2 more. Therefore, it's going to want 2 bonds. Chlorine has group number of 7, therefore it has 7 valence electrons, and I think you're getting the point here probably, that it will want to make 1 bond to get that 1 extra electron. Last but not least here is hydrogen. And hydrogen and helium are our weird exceptions in that they can only hold 2 valence electrons because they only have a 1s orbital. Again, we will talk about orbitals at another time. Not everything can fit in one video. Hydrogen has 1 valence electron that we can see here, and therefore it's going to want to make 1 bond. And it can only make 1 bond. We're going to use that here in the future as we go back to our C3H8. These 3 carbons here need a little bit of help, because if you look at this first carbon on the left here, let's turn his line into dots. He has 1 electron from himself and 1 electron that he gained from his neighboring carbon. He has an additional 3 electrons that come from himself. If you remember, carbon has 4 electrons, so 1, 2, 3, 4. His other empty one was filled by this carbon, and he has 3 more empty spots that he needs to fill. If we bring in hydrogens, they will fill the remaining spots. So he has 2 and 3 hydrogens. That gives us a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. So let's redraw those with lines, because that's how you're going to see them really most of the time. If we look at the other carbon on the opposite side, he has a similar issue. He only has 1 bond, or 2 electrons, there, so he's going to need 3 more bonds. So we will fill those in again with hydrogens. This one in the middle, he has 2 bonds, so he needs 2 more. If we count up our hydrogens here, we see that we have 1, 2, 3, 4, 5, 6, 7, 8, just as mentioned at the top, C3H8. Now let's talk about different types of structures. This one that we have drawn here is called Lewis, Kekule, or structural formula. Lewis specifically is usually connected by dots instead of lines, as we've shown previously in the video, but Kekule and structural formula also work. There are pros and cons to this. The pro is it shows all its bonds. You know all of the atoms that are present, there's nothing inferred here. The con is, with larger complex molecules, it begins to be a little bit hectic, like this one. This is acetyl-CoA, known for being part of glycolysis and the Krebs cycle and all of that. Now, back to the structure here, we can simplify it. We turn the carbons into a line and get rid of the hydrogens. Let's watch that again. Those carbons become each end of the line, and this is really easy to draw. That's definitely one of the biggest pros. It's easy to draw by hand. However, a con is it's hard to draw with a computer without a program like ChemDoodle, ChemDraw, ChemOffice. Another con is that the H's, the hydrogens, are inferred, and so you have to get used to that with practice. You'll have them here, you'll go, okay, this is an end of a line, so I know that there's 3, there's another 2 here, another 3 there. So this one is called skeletal, or bond line. Next, we have condensed formula. Now, if we take this structural formula we had before, we can turn it into the condensed formula, watch each of the groups here. Then we take this next one, and then the last one here. That is the condensed formula. The pros of this is it's super easy to type. No problem at all, as long as you can do a subscript. The con is the bonds are inferred. You have to get used to how many hydrogens there are if it's a single bond or a double bond or triple, which we will get to further in this video. But again, practice makes it so much easier. So this is also a helpful way to draw out things. Now, a quick recap here. The bottom 2 are ones we just talked about. Structural formula, you see all the bonds, everything's there. Condensed formula, we just discussed it. Molecular formula has all of the atoms just counted up. There are 8 carbons in these ones drawn here at the bottom, 18 hydrogens. Empirical formula, on the other hand, is just the ratio. So there's 4 carbons for every 9 hydrogens in here. So going back to the skeletal or bond line, this is going to be one of the most common ones that you will see. So we're going to focus a lot on this one so that you can practice it, learn to draw it. It is very key to your success in organic chemistry that you can read and write these bond line structures. I am actually going to switch over to hand drawings to make this a little easier on myself, but also to show you and help you practice drawing them. Let's start with the specifics of different bonds, and we will visit these more, but first things first, these are the three types of bonds. We have single bond, and that is shown simply by a line. A double bond is shown by two lines, and I bet you can guess what a triple bond is. It's shown with three lines here. Now you may have all three in a structure, both all single, double, and triple all in one structure. You may have one, you may have two, but each of them is represented just by the lines between the atoms. So let's talk about a structure that only has single bonds. I will draw a skeletal drawing, and then we will show you here, you can draw with me, converting the skeletal drawing into a line bond structure. So we will count the ends here. 1, 2, 3, 4, 5, 6. We're going to continue to draw it in a zigzag, and each of those corners is going to be a carbon. 1, 2, 3, 4, 5, 6. I'm going to draw a line showing that each of them are connected. And then we fill in with hydrogens. So this first one here only has one line, one bond, so we know that it's going to need three more. So I'm going to fill those in with hydrogens. The next one here has two. So we're going to fill in with two more lines, giving it a total of 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. And I'm just drawing these lines smaller because I do. It doesn't have to be that way. I make my carbons bigger and my hydrogens tiny because I don't care about them as much. Okay. Now, if we look at these future carbons here, they are also in the middle, just like this one was. This is an end carbon. This is an end carbon. All the ones that are in the middle here have two connections already. So they will need an additional two connections. So we will fill these in with two hydrogens each. And the last one again is an end, so it needs 3 to make a total of 4. Let's move on to a clean page. We have branched single bonds. So if we have a structure kind of like that one, but it has a branch. So this we're going to draw again. We're going to count 1, 2, 3, 4, and then a fifth one attached to the 1, 2, third one. Okay, so we have 1, 2, 3, 4, and then a fifth one attached to the 1, 2, 3 down here. We're going to draw the lines to connect them. And then again, we're going to fill in with hydrogens. An end one, again, still it only has one connection. So we're going to give it 3 more connections to hydrogen. This one, he's a middle guy. He has 2 connections. Just like before, we're going to give him 2 more. And this guy here, again, he's an end. He's got 3. The one that's different in this branch is this guy. This carbon has 3 connections already. So he is going to need only 1 hydrogen to fill his 8. 1, 2, 3, 4, 5, 6, 7, 8. This carbon, again, even though he's the branch, is still an end carbon, and he only has 1 connection, so he's going to need a total of 3. 1, 2, 3 hydrogens. Now, if we want to turn this back into the formula, we can see that there's 1, 2, 3, 4, 5 carbons, so we'd say C5, and then how many H's? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are H12. Okay, moving on here, we're going to talk about rings. So if I draw a hexagon, This still represents carbons, but there are no ends, okay? So we've got 1, 2, 3, 4, 5, 6, of course, because it's a hexagon. We're going to draw this the same. 1, 2, 3, 4, 5, 6. And I'm going to draw the lines in between here. Now each of these is an in-between carbon, each having two connections. So each one is going to have two hydrogens. A quick tip, at the beginning of organic chemistry, teachers will often have a test or quiz question involving a skeletal structure, like this above, and they will ask how many hydrogens are in the structure. I will just start drawing little tiny dash marks on there. Now, you can't draw that as an official drawing because any line represents a carbon, and so you can't draw that officially. But if I were to receive this and say, how many hydrogens are on there? I'd go, okay, this is a carbon, this is two lines connected to it, it needs two more. 1, 2. I'd look at this one, same thing. 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. And then I'd go count up all my dashes. I could write in hydrogens all over here, but half of the time, if I'm just asking how many hydrogens there are, I'm just going to go and count up my dashes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. H, 12, and we know that it's a hexagon, so C6. Now, I just want to make that clear though, never draw this and expect your teacher to know it's a hydrogen. But I do that for myself just to save myself a little time. Now, let's move on to double bonds. We have two carbons here. For them to form a double bond, we need to rearrange their electrons a little bit and have them come together. So now, in the middle there, you see that they are both providing two electrons and they're both gaining two electrons. Then they get hydrogens coming in to form their remaining bonds. So we have two coming in on the left, two coming in on the right. And you see this first carbon, if we count up those, he has 1, 2, 3, 4, 5, 6, 7, 8 electrons. The next guy, again, has the same 1, 2, 3, 4, 5, 6, 7, 8. So both are happy, they have their octet. And this is what it looks like. You've got two lines in the middle and two lines going off to hydrogens. This could also be drawn simply like this. That is your structure. So let's talk more about double bonds here. We could have a structure that looks like this. Okay, and he can draw it like that. There's lots of ways to draw, and I'm going to make a note of that. You might see it like this. You might see it like this. You might see it how I drew it originally. It might not be connected. You'll see lots of things, okay? So no, this is double bond here. They all mean the same thing. And you're going to count 1, 2, 3, 4. That's how many carbons you have. 1, 2, 3, 4. So we're going to draw the lines in here. And then we're going to draw in that double bond by making a second line. That's it. Now we put in our hydrogens. This guy, he's still only got one single bond. He's on the end. You get the picture. He's got 3 hydrogens. This guy, he's got 1, 2, 3. So he only needs 1 hydrogen. So we're going to draw him up here. This guy has the same. 1, 2, 3, 4. You can see he has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And this guy, 1, he's on the end. He needs 3. Now, if we are going to talk about rings, we can talk about them with double bonds as well. And we will talk about this benzene ring. It's called an aromatic. We'll talk more about that later. It's also called conjugated, where we have every other bond being double. Okay, so this is how we draw it. if we're going to draw this in the line bond structure, we will again draw our 6 carbons. 1, 2, 3, 4, 5, 6. We're going to connect them all. And then we're going to draw in our double bonds here. Now, if we look at each of the carbons, we count how many connections there are. 1, 2, 3. So we need how many hydrogens? 1. Let's look at the next one. 1, 2, 3. Again, we only need 1 more hydrogen. And you can assume now that they will all be exactly the same since they all have the same connections. They all need 1 hydrogen. We can go around and count. There are 1, 2, 3, 4, 5, 6 carbons and 1, 2, 3, 4, 5, 6 hydrogens. That is our benzene. Now, as for bonds, last but not least, we have the triple bond. So again, we will restructure our valence electrons here, bring our carbons together, and that forms a triple bond. If we bring in hydrogens to either side, we fill in our last valence electrons, and that gives us a total of 8 electrons here. 1, 2, 3, 4, 5, 6, 7, 8. And again, 8 electrons here. I won't count them again for you. But we turn those into lines, and that is what our regular structure looks like. We can draw it just like that. Now for a triple bond, drawing it with a larger structure than just a single triple bond, we will put in something that looks like this. Now, something interesting about triple bonds is that they are straight. Double and single bonds, they have this zigzag pattern like this, where they form bonds up and down. A triple bond, if we go back here, you can see that they have to be straight out from the sides, and that is how they form. So if we are drawing this structure here, this is a carbon, this is a carbon, this is a carbon, and this is a carbon. So we have 1, 2, 3, 4. 1, 2, 3 bonds in the middle. This one's a triple. And I'll just put in a brief note that this is actually the closest and strongest bond. They're in order. Single bonds are the longest and weakest, then double, then triple is going to be the shortest and strongest, which makes sense if you think about it. You have 3 lines holding it together. Now, back to this thing. If we were to keep going with this thing, we could add more carbons. That's when it starts bending again. So this carbon that comes off of here has to be straight out, and then it starts going up and down again. Okay, so we'll just add these in just for fun, so you see how it changes when it's not around a triple bond. So the 2 carbons have the triple bond, and then anything after them have to be straight out, and then everything else goes back to being up and down and up and down. So again, we can go back to the outside ones. We know that it has 3. I'm not even going to draw the hydrogens this time. This one is in the middle, it has 2. This one in the middle, it has 2. This guy here has 1, 2, 3, 4. So we know that he's already happy. He's good. He doesn't need anything else. This guy too, 1, 2, 3, 4. He doesn't need any more hydrogens. This guy again, 1, 2. He needs 2 hydrogens. This guy, 1, 2, 2 hydrogens. And this guy needs 3 hydrogens. And just because I have so much anxiety from teachers hating that I put lines, I will put that in there for you and to remind you not to do it yourself. Okay, now that is our single, double, and triple bonds. Please come back for more videos in the future so I can talk about how to not only draw them, but how to name them and how to do important reactions. So if you would like future videos, go ahead and like this, subscribe so I can keep getting you more videos in the future so you can pass your chem class.